device that would be able to change the spatial. So in linear optics, it is completely impossible to change, to uncouple the interaction length from the Thank you. It is impossible to uncouple the interaction length from the beam diameter. So they are fundamentally coupled to each other. But luckily enough, there are several possibilities to still work around that problem, and one of them is the waveguide. In a waveguide, when you're coupling your laser beam in a guided mode, you can enjoy a large interaction length, and still your beam diameter can be small enough. Now, another possibility, the waveguiding is one possibility, and standard optical fibers are well known. Now, new fibers, as I said, most of the results that I will be showing will be built up around new technologies that have been developed recently. And one of those technologies developed by Philip Russell and his group several years ago is photonic crystal fiber technology, which allows you to modify the structure of a waveguide to achieve the required dispersion profile and the required nonlinearity. Now you can go even further in terms of the spatial localization of your light field, achieving a high degree of localization and high efficiency of nonlinear optical interactions. And you can go to nano waveguides, localizing your light field within photonic wires and sub-wavelength waveguides. This is another extremely interesting area. And on a different side of the intensity range, in the regime of high laser intensities, it is possible to achieve the regime of propagation which is not really free of diffraction, but with strongly suppressed diffraction, where diffraction is strongly suppressed by nonlinear optical interactions. When your laser beam is intense enough, it can modify the refractive index of the medium, and since the intensity profile, right, you have the non-uniform intensity distribution across your laser beam, and it modifies the refractive index in a material, and it creates a lens for you. So this is how a beam can be focused. And then as it becomes focused stronger and stronger, it generates free electrons, and then the free electrons balance this self-focusing by the self-defocusing, because the distribution, the profile of free electrons gives you a negative lens. So you can have some dynamic channeling regime where the laser beam effectively propagates with strongly suppressed diffraction, and you can maintain this propagation over long distances, the regime that is called laser-induced filamentation. So I'll talk about these regimes, waveguides and filaments, in the context of generating ultrashort pulses. So I'll talk about the physics that helps you to generate very short pulses using those two regimes. And since I promised to talk about physics, I will start with the discussion of the optical solitons and new opportunities that one has due to the solitonic mechanisms of pulse transformation in waveguides first, and then also in the filamentation regime, the regime of filamentation. Of course, solitons has been known for a long time. This is the picture. This is not our work. This is something that I copied from the Nature journal, published in 1995. And this experiment is intended to reproduce the original observation by Scott Russell, a scientist who was the first one to observe the solitonic effect on the surface of water. So it was a successful reproduction of that historical experiment, We are talking about optical solitons. Soliton is an object. In optics, this is a light pulse that propagates essentially without changing its shape in the time domain. And of course, dispersion in linear optics, that wouldn't have been possible because of the dispersion. Dispersion is a fundamental property, right? You cannot cancel dispersion, but you can compensate for the dispersion. Dispersion induces stretching of the pulse, right? Dispersion tends to stretch your pulse, but then you are coming with nonlinearity. What nonlinearity is doing to your pulse, it induces modulation of your field, and it changes the spectrum. It generates more low frequency components closer to the leading edge of the pulse, and more high frequency components on the back of the pulse, on the trailing edge of the pulse, right? And then dispersion it causes the propagation of the pulse in such a way that the trailing edge of the pulse catches up with the leading edge of the pulse. So the pulse essentially propagates without changing its waveform, without changing its shape. So mathematically, it is described by the non-linear Schengen equation. It is as simple as this, includes only 3 terms, and physically, I don't want to bother you with all this maths, of course, but physically, we need 2 effects to generate solitons. We need dispersion, and we need nonlinearity to compensate dispersion. The nonlinear phase shift needs to compensate for the dispersion-induced phase shift. This is when soliton is generated. Now, this is possible in waveguides, especially if you can play with a dispersion profile, then you can generate quite short solitons. But now all the other factors will result in the dissipation of the energy from the solitons, right? So you need the dispersion. Moreover, you need only the second order dispersion. So the frequency profile of your propagation constant, or your wave vector, or frequency dependence of your phase velocity, if you want more physically, needs to be approximated with this quadratic polynomial, second order polynomial in the frequency. If this is not the case, if we are including also high order terms, then our soliton will die off within some propagation length, sooner or later. Now, on the nonlinearity side, the nonlinearity needs to be instantaneous. Otherwise, the soliton will modify. Sometimes this is detrimental, but sometimes it is useful, and I will give you some examples how it can be used for frequency conversion, how it is possible to use this phenomenon to build wavelength converters in a very efficient way. So this picture shows a soliton on the surface of water. Now this picture, this map, this is a space-time map showing the space-time. This map shows the space-time dynamics of an optical soliton. As you are propagating a pulse through a dispersive medium with nonlinearity, then you are generating a soliton. The soliton it develops the dispersion of its own. It propagates with its own phase velocity, with its own group velocity. It does not talk to all the dispersive waves. But, so this is where you can see how this soliton builds up as a pulse of these dynamics. But then because of all those perturbations, because of the high order dispersion, because of inertia of nonlinearity, it starts losing its energy. And then all those dispersive waves are generated. Right? The beauty of the soliton is that it does not talk to the dispersive waves. Right? The waves that solve the propagation, the Maxwell equations for your medium, for freely propagating plane waves. The solitons are not like that. They don't talk to those waves. Ideally, as long as they are described by this nice and simple nonlinear Schengen equation. But as soon as we have more physical phenomena coming into play, then those solitons start talking to dispersive waves, inevitably transferring energy to them. So they're losing this energy, and this is what is seen as in this simple simulation. So here still the soliton can be seen to maintain, to keep its identity for quite some length, but of course it's losing its energy. We have specifically engineered fiber structures to modify the dispersion profile, to prepare the dispersion profile we need for the required type of solitonic dynamics. We're doing this by changing the structure. So those are the cross sections of the fibers made of silica or more complicated glasses for high nonlinearity. So those fibers are the fibers where the light is guided through this central part, which is made of silica or glass. So the light is confined here in the central part of the structure. But we can also have fibers where the light is guided through the hollow core, and this is interesting also from the fundamental point of view, because there's no total internal reflection here in this type of the waveguide, right? Because we have a gas field hollow core, so the refractive index is always lower than the refractive index of the cladding. And if it were a simple bulk medium here, simple bulk material surrounding this hollow core, then the light would have been inevitably leaked into the cladding. But within some finite frequency bands, you can prevent this from happening by engineering, by designing a specific periodic structure, which, due to the constructive interference of all the elementary reflections in the core region, still confines the light in the hollow core. And this is a kind of new mechanism of wave guiding, not total internal reflection, not index guiding.
They do not absorb it?
Well, of course, everything absorbs. You cannot completely get rid of absorption, but modern technologies. But in the cladding of those fibers, you still have the material, and of course, some portion of the field propagates through the cladding as well, because otherwise the mode would not know that it propagates through a waveguide. So it has to have some evanescent field, exponential tails of the fields propagating through the cladding. And those are the sources of loss, right? This inevitably induces loss, the waveguide loss. But this can be as low as dB per kilometer. So you can really use hundreds of meters of the fiber without inducing much of loss. But this, of course, depends on the structure.
What is the size of the
It can also be changed by the technology. Here, this one is less than 1 micron. So this is a submicron waveguide. Here also, right here, those small holes here are less than 100 nanometers. So those air holes here are less than 100 nanometer in diameter. Now here, the diameter of the hollow core is on the order of 10 microns. This is what happens here. But you can scale it, the entire structure. And of course, here you want to achieve a photonic bandgap to confine your light in the hollow core region. So the region of guidance is limited. But this bandgap can be increased, can be expanded, and I will give you some solutions for that. So I have some simple demonstrations how the dispersion can be changed. Right? We are talking about this second order dispersion, group velocity dispersion. This shows how different the group velocities are for the neighboring frequencies. This is what makes your pulse stretch as it propagates through a dispersive medium. We're changing so this is my structure, quite generic structure. This is my central part of the waveguide, and those dark areas are my air holes. And this is my dispersion profile, calculated for this structure. So imagine this is a fused silica, and this is just, those dark areas are simply air holes. And I'm now increasing those air holes, and I'm changing my beta 2 parameter as a function of the wavelength. And the change is quite dramatic. Now I'm inflating my holes even larger, and then this profile also changes dramatically. So now from here you can understand that not only the second order dispersions, the second order coefficient can be changed, but also high order coefficients can be controlled, and this is important if you think about a really short pulse. Now you can confine your light within a very small core using this structure, and you can propagate your light, you can propagate your pulse over large propagation length, and this gives you high efficiency of nonlinear optical interaction. The simplest process is, of course, self-phase modulation. This is a process where a pulse, laser pulse, modifies the refractive index of the material again. Right? This is the first nonlinear optical effect, where when the laser intensity modifies the refractive index of the material. Now, since we have an ultrashort pulse, we have a temporal profile, time domain profile of the intensity, which immediately translates, right? It modifies the refractive index, so the time profile of the laser pulse immediately translates into the phase modulation, right? Because the refractive index is something that determines, that controls your phase. So it translates into a phase modulation, and it expands your spectrum, which would not have been possible in linear optics, right? In linear optics, it's not possible to expand the spectrum. You can only filter your spectrum. So you can do this very efficiently. You can generate broadband field waveforms. You can generate supercontinuum. It's a little bit more complicated than just self-phase modulation in interesting physics, but I'm not going to discuss supercontinuum generation too much, although it's really interesting and important and very successful part of this photonic crystal fiber story. I'm going to discuss solitons. Right? Solitons is the balance between the nonlinearity and dispersion. Now, if we have some delayed part of nonlinearity, then it changes the solitonic dynamics. One part of this delayed nonlinearity, inertial nonlinearity, comes from Raman scattering, when the light induces some vibrations inside the medium, exciting molecules or some structures of atoms. This is exactly what happens in fused silica. And then it undergoes inelastic scattering. So this omega-1, this green photon, is inelastically scattered by those vibrations inside the medium, generating a red-shifted photon, omega-2 photon. Now, with the laser, this is a phenomenon that, of course, has been known since 1928, when it has been discovered by Raman, Mandelstam, and Landsberg. And but in the laser field, this omega-1 field can be strong enough not only to serve as a source for those inelastically scattered field, but it can also provide a pump to parametrically amplify this omega-2 process. And this phenomenon is known as stimulated Raman scattering, as opposed to spontaneous Raman scattering observed in the early days of Raman science. Now, what about solitons? What happens to a soliton when it propagates through a medium with this inertial part of nonlinearity? Now, what happens to a soliton is that the red part of its spectrum can become brighter through those photons, and the blue part of the spectrum becomes depleted, because the blue part of the spectrum provides omega-1 photons, and it generates more omega-2 photons closer to the long wavelength part of the spectrum. And the soliton becomes redshifted as a whole. And this can be made extremely efficient. In some of our experiments, when for that, to make it as efficient as possible, then you have to work on the fiber, really, to work on the dispersion profile, to work on nonlinearity. And then, of course, first of all, you need to couple into a soliton the right amount of energy, right? Because otherwise, if your input pulse is not matched to a soliton pulse shape, then, of course, you're losing a lot of energy because it does not couple to a soliton. Right? The soliton has to have some temporal shape, which will solve my nonlinear Schrödinger equation, and which will satisfy this balance between dispersion and nonlinearity. So more or less, you can always observe this effect. This is strong enough. But if you're really talking about the high efficiency of this effect, then you have to really invest some time and some effort into designing the fiber. And if you're doing things right, then you can achieve more than 90% conversion efficiency. Right? But this is 90%. This is not energy conversion, right? It's not possible as far as energy is concerned, right? Because in every elementary event here, you are losing energy. So maximum you can do, the best you can do, you can only conserve the number of photons, right? Because each omega-1 photon can generate omega-2 photon, but then the energy is inevitably lost. So when I'm talking about my 90% conversion efficiency, I'm talking about the photon number conversion efficiency. So 90% of my photons that have been coupled into the fiber at 1.25 micron central wavelength. This is the output wavelength of the chromium forsterite femtosecond laser. I will get them at 2.2 micron, right, from 1.25 micron to 2.2 micron at the output, and I can have 90% of my photons at this 2.2 micron, more or less 1 micron wavelength shift toward longer wavelengths. You can play different things. You can control this process. You can stabilize this process with respect to the fluctuations of your input pulse parameters. This is all very important if you want to design a practical tool using this phenomenon. And this is what we have been doing for several years, doing those calculations. Now, what those two results are of calculations. They look nice because, first of all, they agree with the experiment reasonably well, and they show what happens, how this soliton wavelength shift happens inside a fiber. So we have a 800 nanometer TISEP-Phi laser pulse at the input of the fiber in this experiment, and then we are not coupling everything into a soliton, so it's not that efficient. Of course, no talk about 90% wavelength conversion efficiency in this case, but it nicely shows where the energy goes. So some energy stays unconverted in the wavelength at the central wavelengths of my laser. Right? This is what I was not able, this is what I failed to couple into a soliton, so it does not shift in its wavelength. But then I have also some soliton which shifts in the wavelength. So this is my spectrum, right? A spectrum as a function of the distance. And this is my time domain picture, also as a function of the distance along the Z, along the fiber. Now here I see the soliton, and this is how it becomes delayed. It propagates slower than what is left at the central wavelength of the laser. And then it starts to generate dispersive waves at a certain point, at certain wavelengths, through some resonant process. This is a resonance through phase matching, because the soliton can generate dispersive waves only where its phase is matched to the dispersive wave. So this is why those bands are so well resolved in the spectrum. But I'm not going into details of that interesting physics, and we want to emphasize the results of our most recent work on how multi-solitonic effects can be used to generate ultrashort pulses. So the whole story started several years ago when in our work at Moscow State University we we characterized the coherence of the solitons with respect to each other, and we found that they generate beautiful fringes. And this means that, in principle, by compensating the group delay between solitons, it is possible to synthesize an ultrashort pulse using a fiber format source, right? So it can be made really compact. Of course, for a soliton that is produced in a solid core fiber, it is difficult to increase the energy, right? Because as you're generating, as you produce more energy, you cannot increase the energy of the soliton that easily, because you will generate another soliton instead of increasing the energy of a single soliton. But with a hollow core fiber, you can go to higher levels of energy, because in nonlinears you are in a completely different range of nonlinearities and dispersion. So we have several proposals how to generate a subcycle pulse using that approach. One of them is to kind of couple the soliton, the field, to coherent vibration of molecules inside a waveguide with a Raman shifting. That's shown here. That's something that has not been implemented experimentally so far. What has been implemented in our most recent experiments is this idea of multi-solitonic dynamics yielding subcycle pulses. And it is demonstrated for solid core fiber here, but the physics will be the same for a hollow core fiber. Now what happens here is that when you generate multiple solitons, those solitons, they propagate through a nonlinear dispersive medium, and they oscillate in time and in space. And at a certain length, they generate the shortest possible pulse. This effect that has been well known, this is solitonic pulse compression, and fiber components for solitonic pulse compression have been designed quite successfully. Now, what we're doing here is slightly different. We don't have this ideal solitonic dynamics where the soliton oscillates in the time domain and in the spatial domain. But what happens is that we are trying to use the third order dispersion and the shock wave, the wave time dependence, the non-stationary nature of wave interaction, resulting in a shock wave, to generate shorter pulses. It is possible through this multiple solitonic dynamics, and the figure of merit can be understood. And in the recent work with those wonderful fibers produced at the University of Limoges in France by the group of Feta Benabid, we've been able to identify certain regimes where those subcycle pulses can be generated for 1.5 micron the pulses at the input. And the fibers, the remarkable property of those fibers. Now here you can see that the cladding of those fibers is kind of unusual. It's not a usual honeycomb structure. This is what they call what looks like a Kagome structure, Kagome lattice. Right? So it provides much broader transmission spectrum, which supports pulse compression to subcycle pulse widths. And this is what has been done experimentally in Vienna. And the spectra at the moment, they agree almost ideally with our simulation. So the dashed line is the simulation that we've done for those fibers. And this solid line is the experimental spectrum. Now, those are the results of simulations. So for experiments, we only have some, at the moment, limited understanding of how the pulse looks in the time domain. But based on the spectrum agreement, the agreement that we have in the spectral domain, we believe that we are on the right way of going to subcycle pulse width using fiber-based technologies. So we're completely based on the fiber technology.
These are probably something like modes of this, different modes of this.
We don't want them to be different modes of that fiber, to be honest. That's a very painful question. We want to stay in the same mode as we go through the entire spectrum. And the first, of course, at the very first point, we were very suspicious about that fiber. And I was the one who was kind of skeptical about this technology. We already had those calculations, those simulations showing that as long as this wonderful Limoges technology enables us to produce this broadband waveguiding, then it should be possible to generate ultrashort pulses through this multiple solitonic dynamics. Because now we are in the right range of fiber lengths, so within some 1 meter propagation of the 1 meter of fiber, we can generate subcycle pulses. But I was skeptical about this spectrum, which seems to suggest that there are different modes excited by the laser. But luckily, this is not the case when this spectrum has been measured with an incoherent source. So probably we are lucky because we are working with a laser, and laser excites only one mode. Because of course the fact that we've been able to generate all those spectra, and the X-frog traces are already short enough, shows, not just suggests, but demonstrates that it's in the same mode. Now, all those peaks are not because of the modes, but self-phase modulation can produce similar structure on the spectrum, because self-phase modulation gives you modulation in the spectrum. So this calculation, at least, was done for a single mode regime. Now, let me proceed with the second part, with the second scenario that helps to generate ultrashort pulses, and this one is filamentation, as I explained it. So we have several key phenomena contributing to this laser-induced filamentation process. One is, of course, diffraction, but then diffraction is suppressed because we have self-focusing due to the positive lens induced by our laser beam through nonlinearity. And then we will have also a negative lens, which is due to the spatial profile of the electron density. It gives you a negative lens. And this is how you can propagate your laser beam over large distances. And it can generate, since it's the intensity is high, you have to be above the critical power of self-focusing, which is for gas media atmospheric pressure, is typically in the gigawatt power range, 10 gigawatts. For solid state materials such as silica, it's in the megawatt range. So you can kind of, in solid state, you can also generate those filaments, but of course you are always close on those experiments to the breakdown threshold. So you have to be careful. So as we propagate a pulse through a medium with dispersion, there are again several phenomena contributing to pulse reshaping. Pulse reshapes, and it's a quite complicated dynamics because spatial dynamics is strongly coupled to temporal dynamics. Right? You have a beam, and now the key effect is that the beam self-focuses. But then you have a pulse, so the trailing edge may focus, and then the central part may refocus, so it may be inhomogeneous dynamics over the pulse. The beam dynamics will be dependent on the retarded time, on the time in the reference frame of the pulse. And it gives a very rich dynamics. So we have diffraction, we have dispersion and absorption, we have plasma-induced loss, we have self-stiffening. This is the shock wave, right? The shock wave is developed here because you have an ultrashort pulse and you have nonlinearity. And nonlinearity is here closer to the peak of the pulse, is larger, the additive, the change in the refractive index here on the leading edge of the pulse, where the intensity is higher, is larger than the change in the refractive index on the edges of the pulse. And this means that the peak of the pulse propagates slower than its edges. So it develops this steep edge of the pulse. No, it never happens in optics. It never happens in optics. I will have some slide on shock waves. So probably we can discuss it when I will have this slide, because we were able to identify the regime where the shock waves in optics can become attosecond waveforms. So I have one slide on that. So self-stiffening is important. It not only develops a very specific waveform, a very specific shape, but it also generates a lot of blue shifting. The cell phase modulation is always there. The pure cell phase modulation effect gives you a symmetric spectrum. And then there's also inertial nonlinearity, the Raman effect. We also have all kind of, if we go to details, we also have all types of four-wave mixing. Different components in the spectrum talk to each other, generating new components through parametric process, controlled by phase matching. We also have this spatial beam dynamics, which is self-focusing. And on the ionization side, there's a lot of interesting physics here on the ionization side. We have multi-photon ionization. Most typically, it's both. It's multi-photon ionization and tunneling ionization. And we all know from the seminal paper by Professor Keldysh that they both are simply different terms of the same ionization probability. Right? So on the edges of the pulse, we have multi-photon process, where a process of involving a certain number of photons dominates over the others, because it resonantly transfers an electron from the bound state to the continuum state. But then when the field intensity becomes high enough, then you cannot distinguish a single process, cannot distinguish a single term in Keldysh's formula, which gives a dominant contribution. But all the terms, they contribute fundamentally equally. And this gives effect to tunneling, and I will talk about tunneling a little bit later. So one possibility is to use these dynamics to increase the propagation lengths and to generate lower order harmonics. So we were involved in this interesting work with the group of Ferenc Krauss and Lefteris Gulermakis at Max Planck Institute, and of course they are pioneers. They are the group that generates the shortest pulses available today, less than 100 attoseconds. But that was a different project. We wanted our pulses to be probably less short, but more intensive. So this is why we used this regime, and we enhanced low order harmonic generation, such as third harmonic, fifth harmonic, and we achieved a regime where the spectra of those harmonics were broadened by through nonlinear processes, through self-phase modulation and cross-phase modulation process, and through the ionization-induced nonlinearities, to observe a broadband spectrum within a very, very broad spectral range, which supports an ultrashort pulse. So the pulses less than 1 femtosecond are generated in that with a pretty high efficiency. So that was harmonic generation, right? Third harmonic generation, fifth harmonic generation. So we're talking about enhancing the short wavelength part of the spectrum. Now, but four-wave mixing is everywhere. So as you are broadening the spectrum, you always have two components in your spectrum, even close components, that can generate a very low frequency component through nonlinear optical process, through this frequency combination process. And this has been also identified in our simulations and done in experiments together with the group of Takao Fuji. The work has just been published. I don't have it here on my transparency. It's a couple of weeks ago in Optical Express, where obviously we've been trying to publish this work for a couple of years. So it came out recently in Optical Express, and it shows that with a filament produced by two color input field, it is possible to generate a subcycle pulse in the mid-infrared, around 4 micron. So the result is that it is possible to generate a broadband spectrum. In fact, the spectrum stretches even further in the to longer wavelengths here. So you can generate waveforms at low frequencies, hopefully also terahertz radiation. Some people do observe terahertz radiation. There's a lot of activity in that area as well. But in this work, it was possible to observe a pulse in the mid-infrared with a pulse width that was shorter.
These are 3 different regimes or 3 different?
Those 3, right? Those 3 spectra. Those are different spectra, right? This is we have a 2-color input field that generates a filament. So those 2 spectra correspond to what we have. This is the fundamental of the laser, of a Tie-Sapphire laser. This is its second harmonic. So we have 2 omega minus omega minus omega process gives you something really low frequency. And this something low frequency is centered around here, around 4 micron. So it's 2 omega minus omega minus omega 4-wave mixing process, giving you a kind of optical rectification, but optical rectification that still is not centered around 0 frequency, but very close to 0 as far as those frequencies are concerned, but still measurable. So this is a possibility of generating intense mid-infrared subcycle pulses. Right, so I promised to address the self-stiffening physics. And it's interesting, and it's always there. And it's especially always there. It's especially important as the pulse width becomes comparable to the pulse cycle. The order of smallness of shock waves in all these dynamics is on the order of the ratio of the field cycle to the pulse width, and this is exactly where self-stiffening becomes important. So in our typical experiments, we can have a nice agreement between our calculations and theory for few cycle pulses only when the shock wave is included. So this is the spectrum where only the self-phase modulation is induced. Now this shock wave, right, important conclusion here from these 2 calculations is that the shock wave enhances the short wavelength part of the spectrum. It generates a lot of blue shifting. This is what always shock wave is doing. Ionization is also responsible for intense blue shifting, so they are kind of working in the same direction, generating components. And now this is the work that Petya Zheltikov is doing here, and we are extremely excited about these results, and they are exactly about shock waves. Of course, the world is full of shock waves. They're everywhere in real life, in technologies, and also in the fine arts. Now, this kind of arts comes from, as I said, simulations by Petya Zheltikov. We identify the regimes where the shock wave effect, right? This is how, the shock waves can generate a very short waveform. This is not possible, by the way, in the one-dimensional case. So in the fiber, it will not be possible to generate any pulse compression through self-stiffening, right, fundamentally. It's only the three-dimensional dynamics where the spatial effects, spatial nonlinear effects, are coupled to time domain dynamics. And where this dynamics is non-uniform along the pulse. This type of scenario can generate shock wave. So those two, this plot here versus this plot here shows how the inclusion of the shock wave term modify the dynamics. This is what happens to a pulse with no shock wave. And the difference is dramatic, especially as your input pulse is short enough. Now, you're generating, as I said, a lot of blue shift, so the frequency, so this is the frequency as a function of z as the pulse propagates. This is not filamentation, by the way. You are not producing well-resolved filament. Moreover, ionization is not very efficient here. So, and what happens to a pulse is that its trailing edge becomes dispersed because of the spatial dynamics of the pulse, leaving this ultra-fast field transient generated by a shock wave, by a shock transient, as a very short pulse. So it can be as short as half of a femtosecond. And of course, the carrier frequency becomes blue shifted a little bit. This contributes to this pulse narrowing, pulse compression scenario. So we are working on identifying the ways to observe this experimentally. Now, what has been done more on a more practical side is the work that we are doing in one of our labs in Moscow, and this is the work where we're using ultrashort pulses generated through different approaches, most often by fibers, because this is the most practical way to generate ultrashort pulses for microspectroscopy, for nonlinear microspectroscopy. And probably I should have shown this animation before. It shows the nonlinearity. Well, it's universal. Right? I can play it almost discussing any transparency. I could play this animation because it shows how the laser field interacts with matter, fundamentally speaking. The first thing that happens is that the laser induces oscillations of an electron. And then, after some time, those oscillations of an electron can excite oscillations of molecules, of atoms in molecules, and then some slower things will follow. But this interaction with an electron in the atomic system, in the presence of a third body, in the presence of potential, gives rise to nonlinearity. It gives rise to many frequencies. Well, it says X-ray at 2 second pulses, but that's not necessarily at 2 second pulses and not necessarily X-ray. It can be anything, any nonlinearity. And this nonlinearity allows the improvement of the resolution in the microscopy, because the nonlinear process is the confinement of the nonlinear process is much stronger than the confinement of the linear process, because everything is only efficient where the beams are focused. So now the question is how to do this nonlinear spectroscopy. One can use laser pulses, longer pulses, usually available from nanosecond lasers, and they produce a lot of heat, and they produce a lot of damage to a cell, and they do not produce a lot of nonlinear signal, because nonlinear signal is dependent on the intensity. Now, with short pulses, you can generate all the nonlinear signals due to second harmonic generation, due to third harmonic generation, fluorescence through two-photon absorption-induced process, and coherent Raman process. All those signals can be produced efficiently with short pulses in a bio tissue without producing too much damage and without producing too much heat. Now, all those animations should play, but they don't, and it's already good that we see some pictures here. So they used to play on my computer. This mouse here playing on the optical table. Now it's in a much better environment in our new lab with this fiber, by the way, here. And the idea is to observe the activity of neurons using those ultrashort pulses and using the combination of nonlinear optical processes. Right now, here you can see how this in this stereotaxically immobilized situation, it feels much more comfortable. And we're using all kind of combinations of nonlinear optical processes, including third harmonic generation, two-photon-induced fluorescence, and then coherent isotopic Raman scattering to basically get information on different types of morphology of brain tissues, because all those methods, they are strongly complementary to each other, and sometimes you can compare images that you can get using ultrashort laser pulses, and you realize that they are complementary, and what used to be the maximum, what used to be a bright spot in the third harmonic map becomes a dark spot in the second harmonic map. And of course, coherent isotopic Raman scattering contributes with its chemical selectivity. So we had several ways of doing this using different lasers, including TASEP-Phi laser, which is a part of this nice multi-photon microscope machine. And this is our home-built chromium forsterite laser. Of course, with the chromium forsterite laser, the advantage is that the carrier wavelength is 1.25 micron. So you can still generate some reasonable light at the third harmonic frequency, because from the TASEP-Phi laser, the third harmonic frequency will be in the UV, and it's not really convenient to work with third harmonic generation using TASEP-Phi laser. So those maps were produced on different areas in brain, using third harmonic generation, second harmonic generation, and this in fact compares to what you will have with more conventional way of imaging using coloring, standard coloring technique. Right, some more animation that does not play, but this is what coherent isotopic Raman scattering gives you using, again, our chromium forsterite laser based home-built machine. Those should also rotate, but they don't. And this is a single neuron. This is a neuron network generated in the experiments on two-photon absorption-induced microscopy. Now, the fiber is here, and we are coming with an ultrashort pulse. We can have different components of the different processes contributing to the success of those experiments here. We can generate solitons inside the fiber because we want our ultrashort pulse here on the surface that gives an non-linear signal. So this is where a pulse should be a short one. So we need to one of the ways to do this is to precompensate for dispersion, to put a chirp on the pulse. But the other possibility is to have an ultrashort pulse all the way through the fiber by generating a soliton inside the fiber. And it is possible to do it in a multicolor way, generating different colors, different signals, both in linear and non-linear regimes. This is, by the way, a linear experiment where the brain is colored by different stains. So this is how you can pick up the signal, giving you information on different functionalities of neurons, and also about the morphology, using a fiber bundle attached to a microscope. So this has been the development that we've been working on for some time with a fiber bundle allowing to do the imaging using a standard microscope. And this slide summarizes more longer-term measurements because it is important to, if we are interested in seeing processes on a longer term, say the process related to long-term memory, then it is important to make measurements within a long period of time. So those are the results, for example, obtained for a mouse that received a stimulus here between the 4th and the 5th day, right? On that very night, the stimulus was induced, and then the activity of some particular types of response has been stimulated by this stimulus. Now, ultrafast photography, the last item on my agenda. Remember my very first slide and my original motivation of producing an ultrafast camera that would be able to capture those ultrafast motion, including the motion of electrons and atoms. So now our system, which we want to make an ultrafast movie of, is electron tunneling. Right, this is what exactly happens to an electron wave function when an electron tunnels. Right, remember, we have an AC field, right? So it is an ultrashort pulse, and then what happens is that the potential is doing this swinging. It goes this way during one half cycle of the field, and then it goes this way during the other half cycle of the field, producing finite width potential barrier, which allows the electron wave function to leak into the continuum from the ground state, from the bound state, not necessarily ground state, but from the bound state and into the continuum. And then it tunnels, and then it's free. And then you have a free electron current. You can measure free electron current, and there was some pioneering experiment by Ferenc's Krauss group who were able to measure the electron tunneling, right, related to the leakage of these electron wave functions through this finite width potential barrier by measuring the electron current, by using an instrument that measures electron current. But of course, if you're interested in observing this process, say inside a solid state medium, inside a transparent dielectric, of course, there's no way to measure the current of electrons. There's no way to measure the electron yield inside the solid state. So the idea, therefore, motivated with that, we had an idea of performing measurements in an all-optical way, right? And exactly the way it is shown here. Right, with one pump pulse and then with probe pulses, but without attosecond pulses, using a field half cycle as an attosecond probe. So this has been done by harmonic generation. Now, what happens to an electron? Here, this nice movie again. What happens to an electron here is that when it is ejected from the atom, then it interacts with the probe field, and it produces phase modulation. And the phase modulation, again, because of this movie, right? It is quasi-periodic. You have more electric current, which is localized to the maximum of the field, not to the pulse, right? So it's field sensitive, not envelope sensitive. So every field half cycle, you have maxima you have the peaks of the electron current. And this translates into phase modulation. And this gives you odd order harmonics, no even order harmonics. If it were cycle periodic, then it would have been also even order harmonics. But since it's half cycle periodic, then you have only odd order harmonics. So you have omega plus 2 omega gives you 3 omega plus 2 omega gives you 5 omega. So we worked for several years to get this signal separated from other sources of harmonics, and this finally worked nicely in experiments with the group of Andreas Baltushka in Vienna, and Sasha Mitrofanov was there for those experiments, and now he's back in Moscow, and it was done with this again in this pump and probe scheme. And the harmonics that are generated this way, the whole idea is that the higher the field is, the larger the contribution of high order harmonics compared to the low order harmonics is. And so by looking at the spectra of high order harmonics, by looking at the ratio of, say, fifth harmonic to the third harmonic, and then seventh harmonic to the fifth harmonic, you can extract the information on how fast electron tunneling happens. So this is what has been done experimentally in the gas phase, and the same scheme works very nicely also in the glass material and in fused silica. So this closes my talk. So with these new regimes of ultrashort pulse dynamics, where the spatial effects are strongly coupled to the effects in the time domain, where it is possible to localize the light field both in space and in time, and it is possible to suppress diffraction effects in different ways. It is possible to observe, as a result of this strongly coupled spatio-temporal dynamics, it is possible to identify regimes where pulse compression is enhanced, and it is possible to generate single cycle pulse widths, and even go beyond a single pulse, generate a subcycle pulses, and I give you examples how this can be done with on the fiber platform, and how this can be done using the filamentation assisted beam dynamics. And we are using those tools in microspectroscopy with a specific focus on neurophotonics, and we are working on the development of the ideas of ultra-fast imaging of fundamental dynamics of electron tunneling. And right, so I also had somewhere the group of people who contributed to this work, but it's here. Right, and this is my favorite transparency. Thank you.
What kind of material you use to observe this electron tunneling? You mentioned Aleksei.
It was, I've shown two experiments. One is the gas phase, which is argon. But it is not really important. It can be argon, xenon, krypton, works in almost anything. But then the solid state material was also a range of materials, from fused silica to some ultra pure glasses. We had Leonid Glebov working with us on that. So he provided some really ultra pure glasses where we were able to go to high intensities without producing too much damage, because of course damage in the glass is always induced by defects. And so you have to have, it's always a good idea to have an ultra pure glass to go to high intensities to observe more nonlinear signal, to get more information.
Well, since it's already going to be kind of late, I suggest that we continue our other questions offline, and let's thank